I have a pen. I have an apple. Apple pen. I have a method. I have some electric. Electromagnetism. Hi, my name is Jack Dong, and in this video, we are going to talk about Maxwell equations. Have you ever had experience of crosstalk on the phones with your friends, like clicking noise, or randomly picking up others speaking? Have you ever wondering how the wireless charging is possible nowadays? Do you know that they are actually following the same principle as a power generator and a motor? They are all using Maxwell equations. In this video, we are going to talk about one of the simple Maxwell equations, which is related to the behavior between electric field and magnetic field. So first, we are going to understand what is electric field and the meaning behind it. We will introduce a concept of voltage and how the voltage related to the magnetic field strength. And secondly, we are going to introduce the concept of magnetic field, especially magnetic flux density, and how this could relate it to voltage. There are a lot of similarities between electricity and magnetism, and here are some simple examples of it. For example, electricity, like charges repel and unlike charges attract. There are similar rules in magnetism, like poles repel and unlike poles attract. Moving charge can create a magnetic field, and moving magnet can induce a charge to flow. And the electricity can be used to power up a motor. If we turn the motor around, we can actually produce a turbine power plant. So this is all the quantitative similarities between electricity and magnetism. Is there any relationship between them quantitatively? So today we are going to introduce this topic with one of the Maxwell equations called Faraday's law. It looks complicated, but let's break it down into smaller parts. We will look at the left-hand side of the equation first, which is related to voltage. So the left-hand side is equal to voltage, V for short. So we can say V is equal to the closed loop integral of the electric field by its distance. And let's break it down into simple terms. So voltage, speaking about voltage, voltage is work done per unit charge. So if we write an expression, V is equal to W over Q. We know in high school, work done is equal to energy transferred. So voltage can also be defined as energy transferred per unit charge. If we have a loop and we have a battery, for example, the voltage between the positive node and the negative node of the battery is the work done in moving this charge per unit charge around this circuit. But what exactly is work and how the work done can be represented in this circuit? Let's go back to the example of like work done we learned in high school. Work done is equal to force times the distance moved in the direction of the force. In the right-hand side example, when a man pushes this heavy object, the first time he fails, the object stays in the same position, so the distance moved in the direction of the force is 0. In turn, the work done is 0. So he tried again with a bigger forces, and this time the object moves. So this time this has a force and also has a certain distance move in the direction of the force, which means there is work done involved in this situation. Let's consider another example. When you carry a handbag, into school. In this case, you have force and also you move a certain distance. However, as the force and distance are perpendicular to one another, there is no distance moved in the direction of the force. In this case, work done is also 0. Surprise? So, can we generalize this situation? Yes, we can. Work done is equal to force times displacement times the angle between them, which we can also use a formula. W is equal to F times D times cosine theta, which theta represents the angle between the forces. In the right-hand side diagram, it shows clearly how these three variables are related to one another. First of all, you need to have a force to have a work done. and then you have to have a distance moved in the direction of the force. Or at least there will be a component can be decomposed in the direction of the force. And the angle between them is theta. In this way, we have work done. Or we can write this as a vector dot product, as force dot displacement. When you see a dot product, that means this equation takes the magnitude of these variables, so the f will be changed to its magnitude of f, and the distance d will change it to the magnitude of the d times the cosine theta in between of them. So yeah, vector product. Okay, after getting a concept of what is work done, let's go back to our case of the electric field. Imagine we have a positive charge entering into a parallel plate which produces a uniform electric field, and a positive charge perpendicular entering into a uniform electric field. It moves from the position of A to the position of B because like charges repel, so it repel and it attract to the negative plane, which is following the direction of the electric field. In this case, there is a single force on this charge, which is the electric charge. It is pointing downwards, the same direction as the electric field. The magnitude of the charge is equal to the electric field strength E times the charge Q, or with the following expression, F is equal to E times Q. Okay, so now we have a force, and then we have a displacement, and then we find out the angle between them. So we have a work done in this case. Reminds ourselves of work done's formula from previous slides. It's force times displacement times the angle between them, which is F times D times cos theta. In this situation, the theta is the angle here. The angle here. And when you times D with cosine theta, so it reminds you the cosine theta is this one. If I call this A, call this B, and call this line C, the cosine theta is equal to A over C. So in this way, D times cosine theta will change to A, which is this downward pointer. Okay. Well, surprisingly, this D times cosine theta is in the same direction as force, as the force F exerted on the charge. It looks like a surprising result, but actually it's not surprising at all, because it is when the force, it is supposed to be times on a quantity that is in the direction of the force, and the D times cosine theta will decompose the direction of the movement, the displacement, into a vector that is in the same direction of the force. So this is how our work done is being calculated. Okay, and then we can also write this in the form of dot product, or called vector product. Okay, from previous slides, we know W is equal to Fd times cosine theta is equal to F dot D, which is to vector product. And we also know F is equal to EQ, which E represents electric field strength. Since we know F is in the same direction as E, so we can write a vector formula of F is equal to E times Q. And then we plug in this result back into the previous formula. We have W is equal to E times Q times D, or we can put the Q, a scalar, in front, is equal to Q E dot D. Okay, in the previous case, we are discussing uniform electric field, which is the same E everywhere between these two parallel plates. But what is the situation will become when we have a non-uniform electric field? For example, like the right-hand side picture shown here, which shows a positive charge creating electric field, is non-uniform, which means the electric field strength at point A, EA, is not equal to the electric field strength B at point EB. Then what shall we do in this case? So E is no longer a constant, so we need to use integration. We assume when the displacement D1 is very small, the electric field strength E1 doesn't change. So we assume when this positive charge moves a small amount of distance, this doesn't really change the electric field strength. Okay, so which means that we can still use back our previous formula to calculate the work done. In this case, the work done is W is equal to Q times E1 times D1. Okay, for the second case, the charge moves again a small distance. Okay, we can repeat this same procedure for a small distance of D2, D3, and blah, 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 until we find all the small distances available. So W is equal to Q times E1, D1, E2, D2, E3, D3, and so on. Or we can write it as a summation. If we divide the distance between point A and point B into n segments, and then we sum them up, we will have the following equation, which is from I is equal to 1 to n ei dot di. However, if d, the displacement vector, is infinitesimally small, which is so small that we can have infinite amounts of small displacement between point A and B, then this is going to produce the exact work done involved in this case, which is this formula. W is equal to Q when the D1 is infinitesimally small, approaching 0, and integrated from A to B. Okay? So in this way, we can calculate work done as a finite integral from B to A, which is E with a vector product with the small distance dl. As voltage is equal to work done per unit charge, sorry for the typo here, the V will equal to W over Q. So we can cancel out the Q in this case because we will divide W with Q, and the charge Q will cancel out, leaving this behind, which is E times dl. Okay, let's compare what we have here. V is equal to the finite integral from A to B with E dot dl. And the right-hand side of the Maxwell equation we want to get. Clearly, there's a difference. Where's this circle? Okay, the circle means a closed loop integral. What does a closed loop integral mean? Well, let's explore it in the case of a battery. A closed loop integral means you're starting from the same place, and then you ended up with the same point in the loop. For example, we start from the battery, we loop around the battery, and then we finally ended up in the same point where we started. In this case, we called it a closed loop integral. This is in contrast with the concept of open loop integral, which in this case, we go from the positive node, the anode of the battery, we come to the light bulb, and then we stop here. This is called an open loop integral, okay? So in this case, it means a closed loop integral, i.e. the voltage across the battery, which is represented in the left-hand side of the Maxwell equation, or called Faraday's law. Okay, after explaining the left-hand side of the equation, we'll move on to the right-hand side of the equation. The right-hand side of the equation describes the things related to the magnetic field, which means a change in magnetic field will induce a voltage. Let's see how they are related. So first, let's remind ourselves with the simplest concept, which is B, representing magnetic flux density. Imagine we have a magnet, and the magnet has many magnetic field lines coming out from the North Pole, and then it will come back into the South Pole. The magnetic flux is a measurement of the number of magnetic field lines passing through a certain area. For example, if I put an area here, and then there will be approximately 2 magnetic field lines through this area. And if I draw a circle around here, it will be 1, 2, 3, 4, 5. There will be approximately 5 magnetic field lines crossing here. In this case, the second circle, the second surface, will have a larger magnetic flux than the first case. And let's introduce ourselves with another concept with magnetic flux density, which is magnetic flux per unit area perpendicular to the B, which is the magnetic flux density, which is normal to the plane. Okay, I should say A here. B is equal to phi B over A, where the phi B is normal to A. So basically what this means is that when we have some magnetic field lines, which is perpendicular to the area A, the magnetic field density means like how many of them on per unit area, right? It's like a density. Like when we say about ring density, it means like, oh, it could be intense or it could be light. It means like how many of them fall on a surface per unit area. So we divided the previous quantity, magnetic flux phi B, with A, when the phi B is normal to A. And then we get the magnetic flux density, which is B. And it has a unit of Tesla. Okay, let's discuss two cases. The first case, the magnetic flux is perpendicular to the area. The magnetic flux is perpendicular to the area. In this case, the magnetic flux phi B is equal to B times A because they are perpendicular to each other, B times A. However, what will be the case if B is not normal to A, which means like A is looking like this? In this case, the magnetic B, there is non-magnetic field lines perpendicular to the area A. So in this case, the phi B will be equal to 0 because even though we have B and we have A, but they are not perpendicular to each other. So in this case, it's going to be 0. Can we have a generalized case for these two scenarios? The answer is yes. We can introduce a similar concept like the vector product before. So when phi B is equal to BA, when the flux phi B is normal to A, which means the magnetic field lines is perpendicular to the surface. However, when it's not perpendicular to the surface, but also not parallel to the surface, there is an angle in between these two. We can give the angle a term of theta. And then we decompose this vector component B into two vectors. One that is perpendicular to the area, which is B times cosine theta, and one is in parallel with the area, which is B sine theta. In this way, we can decompose the phi B into two cases. For the perpendicular case, it will just equal to B cosine theta, which is the new magnetic flux density B slash times the area A. Okay, this is for the perpendicular amount. For the horizontal amount, as what we've seen previously, it will be 0. So we can summarize this equation as phi B is equal to BA times cosine theta, where B is a magnetic flux density, theta is the angle between the magnetic flux lines and is perpendicular, as shown here, and A is the surface area. Linking back with a previous case, we can clearly see that this one seems to follow a vector dot product, or called vector scalar product as well. So we can also write it in this form, which is a dot product form, where B is equal to the magnetic flux density of vector, A is an area, which is a vector, and area, how can area be a vector? Okay, area has a magnitude, definitely. For example, this circle, we can calculate it by pi r squared as its magnitude. But we can manually give it a direction. For example, we say in a direction that is perpendicular to the area, we count it as plus, which is positive. When it's on the opposite side to this circle, we count it as negative. So we arbitrarily give A a direction, which is normal to the area, shown with the blue line here. Okay, so then we can say the magnetic flux is equal to B times A times cosine theta, or dot product between B and A. Okay, In the previous case, we are all speaking about constant magnetic field, which means the B is a constant. The magnetic flux density is a constant, for example, in between of parallel magnets. But what will be the case if the magnetic flux is no longer a constant? For example, we want to find out something here. Then we can use the similar concept as before with integration. We assume with a smaller area, A1, these are very small, the magnetic flux density on this very small area, A1 doesn't change, it's still B1. And then at this instant, phi B1 is equal to B1 times A1, okay? And then we pick up another plane as B2, B3, and B4. Okay, so we repeat this one for B2, B3, and B4. We pick up other planes as A2, A3, and then they are corresponding to B2 and B3. And we added them up. And we can also form a summation equations similar to before. Okay, we got this expression which summing up all the small area, infinitesimal small areas around the loop. When each area A is becoming infinitesimally small, the equation will become phi b, which is equal to limit ai to the 0, like this. The ai is so small that would have infinitesimal, these small areas, components, and they will have infinite component of b times a. In this case, we no longer write it as a summation form, we change it to an integral form. Then phi b is equal to the surface integral of b with ds, which ds is represented by a smaller area A. Okay. Let's compare with these two expressions. So first of all, we see it is very close to the right-hand side part of this part. And this circle, what's the meaning of the circle in this expression? Well, the circle in the expression means closed surface integral. So for a closed surface, it means that it encloses a finite volume, like a sphere, like the football. Yeah, UK is famous for football, and football is a typical example of a closed surface, which encloses a finite volume. Or the other example we could say is a whole egg shell. Imagine we have a whole egg, and the shell around it can be considered as a closed surface. On the other hand, the open surface is a surface that doesn't include a finite volume, which could be a lampshade. For example, your lampshade is not really closed. So the point inside here, it can move straight out from the top or straight out from the bottom. This is not called a closed surface, it's an open surface. So it's this case. Or half of an eggshell, imagine you punch an egg, and then you have 50% left of an eggshell, the other 50% is broken down. So basically means if there's a particle inside, it can escape the eggshell directly. So it's not enclosed a finite volume. In this case, we call it an open surface. So we know the right-hand side, it must be a closed surface integral. And this term will mean the total magnetic flux through the area, okay, through the closed surface, I should say. Yeah, through the closed surface. And the left-hand side represents a voltage. So how does these two relate to one another? It's related to by the rate of change of the total magnetic flux. So basically it means a change in magnetic flux will induce a voltage. And the voltage will drive an electric field, drive the electric charge around the loop. And this can cause energy transfer. So for example, if we have a coil here with a light bulb here, and then we drop a magnet down into this coil from the top to the bottom. In this case, the B.ds around this coil, okay, initially, when the magnet is infinite far away from this coil, it's gonna have this term, the total magnetic flux through this area is going to be 0. However, as a magnet approaches this coil, there will be some magnetic flux passing through the coil, right? As shown here. In this case, there will be some induced voltage within this coil. Then the total magnetic flux is no longer 0. It's going to be a positive number, right? Something positive. In this case, the total magnetic flux through the area will change from infinite distance away from the coil to some distance around the coil. So this change in magnetic flux will induce a voltage. And this induced voltage will have the capacity to drive the charge around by generating an electric field causing an energy transfer. The same thing will happen as a magnet leaves this coil. When it's reaching the end of the coil and it's gone. Okay, in this case, the magnetic flux will gradually drop down from a positive value down to 0. In this case, it will generate an opposite voltage. However, if we have a coil and we are very lazy, so we just leave the magnet here and we do nothing, then will it generate a voltage? No, it will not, because it only happens when there is a changing magnetic field, which means that when the magnetic field is constant, the total magnetic flux is constant, it's not gonna generate any voltage at all. Okay, the other interesting thing is the minus sign here. The minus sign indicates the induced voltage is opposing the changing magnetic flux, which means if you if you drop down a magnet into the coil, the generated current or the voltage will be in the direction that's opposing the change of magnet, i.e., when the magnet falling down into this coil, the current generated will be in a direction that is opposite to the motion of the magnet, which will produce a force F on this magnet by the electric field. Think about this in another way, like energy should be conserved. When the magnets drop down through the coil, the kinetic energy will have to be transferred into somehow to power up the light bulb to generate the current. The current cannot be generated from nowhere. It has to from somewhere by the law of conservation of energy. In this case, the kinetic energy of the magnet is changed to the electrical energy in the wires, driving up the light bulb. So this minus sign is being noticed by Lenz's law, by a person called Lenz. He said the direction of the induced current is always opposing the change in the magnetic field. That's where this minus sign is coming from. Before the end of the video, let's do a quick summary. The left-hand side is a closed-loop integral between the electric field strength and the distance moved throughout dl. It is equal to the rate of change of the total magnetic flux through an area, okay, with a closed surface. And the minus sign here indicating these two are generated in the opposite direction, which opposing one another. Okay, this is the end of the video. Hope you like it. If you have any suggestions, don't forget to leave a comment below. And if you like this video, please give a thumb up and subscribe. And I hope to see you soon. Bye for now.